Okay, good afternoon, everybody. I hope everyone's having a wonderful day. So just before anything, just as a reminder, remember that there's the take-home test, the first take-home test. You will have essentially since last night at 12 a.m. last night until the end of Sunday to hand in your take-home test. So this is all being completed on your courses on our course website. And just the few recommendations, take a look at the instructions and read them carefully. And of course, when it comes to the problems, make sure, as I said, read it carefully. But if you're not sure about how to answer the question, remember, this is technically an open book test. So if you find yourself needing to go back to the lecture notes or the lecture videos or want to look at the textbook, that's okay. That's all fine by me. It's an open book test. Just obviously don't talk to your friends about the problems until after Sunday. But other than that, I want to wish you the best of luck on it if you haven't started yet, or if you have started, I want to wish you the best with it, okay? So the whole point of these take-home tests is to help you see the kinds of problems I can ask you, say, on the final exam. So anyways, are there any questions before we get started, or are we all good to go? Give me a thumbs up if we're all good to go. I think we're all good to go. So let's start talking about an interesting topic in its own right. I think it's an interesting deviation from what we talked about last day, when we talked about ambiguity, and we had this issue with context-free grammars of ambiguity. Now, this won't exactly fix that problem, but this is often a strategy that people use, is they'll like to have context-free grammars that have a much more simplified form. Because context-free grammars, as you've seen from the examples we've done up to this point, there are a lot of ways you could express a context-free grammar. It's very flexible. But wouldn't it be nice if we could take a context-free grammar and put it into a much simpler form, so that whether we can encode that context-free grammar in a much more simpler way, or we can use this context-free grammar in a much simpler encoded way so that we can feed it to some algorithm. So that's where Chomsky Normal Forms come in. So this is one of the simplest among useful simplified forms of context-free grammars. And the definition isn't really too complicated, but I want to explain briefly after I do this why you might consider this form. So imagine I'll tell you that a context-free grammar is in Chomsky Normal Form. So if you're wondering who's named after, it's named after Noam Chomsky. This is from the late 50s, early 60s. When this is one of Noam Chomsky's kind of like, we poke at that's like one of Chomsky's big contributions academically, is along with a lot of his early language work. This Chomsky Normal Form, at least that was the intention of it at the earliest times. We use it a lot in computer science for not necessarily the exact same purposes. It's more of a linguistics thing from Chomsky's perspective. So we call a context-free grammar Chomsky Normal Form if it satisfies one of the following forms for each of our productions. So there's 3 of these here. So what it has to be is that every one of my production rules, it has to fit one of these 3 rules. So the first one is that I have a variable on one side, the head of the production, and then I have 2 variables in the body of that production. There's the second form, which is I have a variable, and then I have a terminal, just a single terminal on one side. By the way, we usually refer to productions which only have one symbol in them. We call those unit productions. In contrast, something like this is what we would call a non-unit production because it has more than one symbol. But notice the form. This one consists entirely of variables on the right side. This one consists of only terminals on the right side. Now we have this third one here. This is where we permit the start symbol to have a production which includes epsilon. This is the only exception where we're allowed to have epsilon. So now you might ask, okay, are there any constraints on these A, B's, and C's? Well, A, B, and C are just any variables in the context-free grammar, and A is any terminal. But I must stress that B and C are not the start symbol. But here's the idea. I want you to kind of revisit the idea of the parse tree in your head. So remember when we did a parse tree, or at least when we talked a little bit about parse trees, remember we had it where, okay, you imagine you have the start symbol, and then you apply the production rules, right? Well, imagine I had something that looks like the Chomsky Normal Form. I'm just kind of just doodling this for you just to give you an incentive or idea of like why we might want this thing. So imagine I have, say I have A. So suppose I have A like this. So I imagine I have some start symbol A, sorry, S, and then I get A. And say if I read in B and C, hypothetically speaking, and say each one of these has some terminal off of it. I don't know, I'll call them D and E. Is there any special property this parse tree has? There's a special name for these kinds of trees. It starts with a B. Think back to data structures. So think about it. The parse tree has how many children for any one of the internal nodes? How many children at most? 2. At most 2, exactly. So it has a structure that's a binary tree. Is that wonderful? So now you have something that's a little bit easier to work with. And we know how to do things with binary trees, right? So like you do all sorts of fun stuff with binary trees. We love trees, especially binary ones. So imagine you have something in this form, then this is something much easier to encode and use. For example, for some algorithm. Say, for example, you want it in the form of this so you can encode it as some binary tree, and then you can feed that to some algorithm. That's one idea. There do exist other algorithms out there that do use as input a context-free grammar that's in Chomsky normal form. If I have time later on in this course, I might address this at some point. I probably will, but I might not be able to go into all the details of it. But the point is that these nice simplified forms have all sorts of neat applications for them, but it also gives us a nice standard way we can always take a context-free grammar and transform it into that form. So here's the idea, is that any context-free grammar can be generated or described by a context-free grammar in Chomsky normal form. And you might ask, how exactly do I do this, or how do I know this? Well, I'm going to give you a way to take any context-free grammar and turn it into a context-free grammar satisfying the Chomsky normal form. So that's what we're going to be doing today. So depending on how far we get, we might see a bit more today, but let's talk about that. So are we all okay with the Chomsky normal form? So remember, it has to satisfy these 3 rules for any one of the production rules. Just remember, so just keep in mind that in the back of your mind as we're doing this. So I'm going to, what was the question? Oh, why is it called normal? Yeah, so there are different kinds of normal forms. These are just meant to be saying, hey, look, if I want to have, so the best way I could describe it is, imagine you had some convention you wanted to follow, and you want everybody to follow your convention. It would be nice to have some way you could describe to other people how you should follow that convention. A normal form is a way I could describe, say, for example, a context-free grammar. But there's several different ways you could use the phrase normal form. In this context, what I'm saying is it's the normal form that was given to us by Noam Chomsky. So it's usually attributed to Chomsky. But there's different kinds of normal forms that exist for context-free grammars. There's plenty out there. For example, there's another one called Greibach normal form. That's another one that's kind of related to Chomsky normal form. But there's several of these normal forms. The whole idea is that the normal form provides you some standard for which you can say, hey, look, every single part of my context-free grammar, or if I was talking about some formal construction, it's always going to have this specific form. And usually this normal aspect is just to keep it in a line in a specific way. Now, I don't want to get into too many technical details about properties that this normal form has, but I most certainly, hopefully that'll give you an impression. So the whole idea is that it's some way I could say, hey, look, if I can ensure it's in this specific form, I can guarantee certain properties. That's why I usually like to have it. Just like I talked about, like I could take anything that's in Chomsky normal form, its parse tree will look like a binary tree like this. So hopefully this will give you an idea, but there's several ways I could deviate on this conversation with this. I'm trying my best to just give you just a flavor. So anyways, what I want to do is I want to use a running example to help us walk us through this process. And I must stress that I'm going to show you a series of algorithms or procedures. They're going to form a series of steps that we're going to apply. And we're going to do one after the other to take this context-free grammar. And you can do this for any context-free grammar. I'm just going to use this example. Does anybody remember what this example, what does this context-free grammar represent again? Yeah, palindrome, exactly. So this will allow me to generate any string that's a palindrome, right? Or binary string, to be more precise. So what I'm going to do is I'm going to take this, because this is not in Chomsky normal form. Does everybody see why it's not in Chomsky normal form? Can somebody point? So tell me, which one of these, or at least one of these, is the problem? Can somebody show me or tell me? Is it, say, this one? Is this going to be a problem for the Chomsky normal form? Yeah, this one's definitely going to be a problem, because notice it has terminals and it also has one variable here. So notice that there's 3 symbols in this production rule, but it also consists of terminals and variables. So that definitely does not fit the form of one, which was just simply that I have two variables on the right side. Neither of them are the start symbol. Likewise, this one's also a problem for the exact same reason. This one's okay. That's okay. This one we'll have to think about, because technically it is actually a part of the start. And this, for our example, it's not so much of an issue because it is associated with the start symbol. But you're going to see, as I'm going to do this process, that epsilon is going to get kind of shuffled around a little bit. So technically, the problem with this right here are these 2 production rules. That's why it's not in Chomsky normal form. So what I'm going to do is I'm going to perform a series of operations, which are really just algorithms. And I'm going to walk us through transforming this into one in the Chomsky normal form. So I'm going to put it in the Chomsky normal form. So here's the idea. So just to make it a little easier for me, I'm just going to for any context-free grammar, and I'm just going to assume it has the variables, terminals, productions, and a start symbol. So that's what it's going to initially start off as. But in our case, we'll substitute in the variables, the terminals, the productions, and the start symbol. So I'll let you do that if you'd like. But I'm going to proceed with the following steps. So this is the first one I'm going to do. I'm going to use these labels because they tend to be a convention these days when teaching the Chomsky normal form. What we want to do, just to guarantee, because remember, I must stress that this process will guarantee that the context-free grammar is in Chomsky normal form. There may be things that you can always do to alleviate some of these rules for specific context-free grammars, but I'm going to give you a general process we could do always to get a context-free grammar put into Chomsky normal form. So this is the first step. This is the easiest one. So all I do is I make a new start symbol. I make a new start symbol. I'll call it S0. And add the rule S0. It's going to give me, so I'm going to introduce this production rule, S0, production symbol, S. Remember, S is the start symbol. So in our example, it would be A instead of S. So you might ask, Dan, why do we need to do this? This will guarantee that anything that appears on the right side of any production rule will not be the start symbol. So I'm going to create a brand new one. And that way I can guarantee that none of the productions that will appear anywhere else in the grammar will exactly have this new start symbol in it. So just to continue our example, I'm going to take this right here. I'm just going to introduce the start symbol, S0. I'm going to give it A, and then I'm just going to leave everything as I had it before. There we go. So Isn't this step really easy? This is the easiest step of them all. Just always remember this one. This is the easiest one to remember. You just do this out of instinct. Okay, now the next one is also not too terribly bad either. So I'm going to refer to this as term, just as an abbreviation. So what we're going to do is we're going to eliminate productions. We're going to eliminate productions with non-solitary, not non-solitary, non-solitary terminals. Now you might ask, what the heck does that mean? Let me explain. So some people like to say that if you have a production rule where, say for example, right here I have a terminal right here. It's on its own. Some people will call that a solitary terminal because it's all by itself. That means a non-solitary terminal means it's hanging around in one of these production rules over here with at least some other stuff. So there's some more symbols there. So there's some terminal hanging around with the rest of a bunch of symbols. And I would like to get rid of these from those production rules, because I would like to have it so all of these production rules that have more than one symbol, at least these ones in particular, at least, I would like to get rid of all the instances where terminals appear. I would like to turn those into variables. So you might think, okay, well, how can I fix this? Well, here's an easy way. Here's an easy way I suggest doing it. Is we take each one of our terminals and we're going to introduce a variable for each one of the terminal symbols, if it doesn't already appear as a rule that all by itself. I'll get into that maybe if I have time. But the point is that you're just going to introduce some new productions with a new variable for each one of your terminal symbols. And now, because if you have a production rule with a new variable, you can use that variable that represents your terminal and you can substitute it in everywhere where you see that terminal appear. In one of these cases where I have non-solitary terminals. So I'm just going to sort of drag them out into their own rule. So here's the idea. So introduce a new variable. Introduce a new variable. I'm going to call it XU, but you could call it whatever you like. I'm just calling it that to make this easier to communicate. XU for each U in T. Remember, that's the set of terminals. And add production. So we're going to add production XU U. So that's the first part. I just take each one of my terminal symbols, I'm going to introduce a new variable, and I'm going to add a new production rule in for it. Now the second part of this is quite simple. For each non-unit, so remember that means it has more than has two or more symbols in its body. So for example, this is non-unit, that's non-unit, this is unit, that's unit, that's unit. If it has two symbols, it's non-unit. It has, for each non-unit, as in it has at least two symbols. Just to be clear, it has at least two symbols. That's what non-unit means. For each non-unit production rule. For each non-unit production rule. For each non-unit production rule. Where U appears. Replace U with XU. That makes sense, right? You just replace everywhere where you see one of those terminals in one of these non-unit productions, you're going to replace it with our new variables we introduced. That will make sure that there's no terminals hanging around as buddies with the variables. And you might say, why? Well, it's because remember, if, say, I give you a production rule and it only has one symbol in it, there's no if it has a terminal, then it has a terminal, right? If it has a variable, that just simply means, hey, look, it's just a variable hanging out by itself. That's no problem. Yet. Yeah. I'm getting to that. So let me continue the example. First, are we okay with this step? This is another one of these steps. It's not too bad at all. So once you see the example, it should click quite nicely. So back to our example. So we're going to, because I have a 0 and a 1, all I'm going to do is I'm going to introduce new variables. I'm going to introduce new variables. I'm going to call them x0 and x1. x0 and x1 for terminals. Terminals 0 and 1. So naturally, I have to create new rules for these two using those variables. Add x0, it produces 1. Sorry, no, it produces 0. I'm just using my subscripts. I better follow those. We always have to be careful of these things, okay? x0, it produces 0. x1 is going to produce me 1. Then substituting those variables we get. So I'm going to just simply take what I had before, and I'm just going to inject the new production rules with those new variables, and I'm going to make those substitutions. So I have S0, which will produce me A. Let me get to A in a moment. Remember, I have x0 is 0, x1 is 1. And then, of course, I need to put each one of these into my non-unit productions, right? So where I had a 0, now I'm going to put x0 there. And I put an A. Then I put an x0. For this case here, I better substitute the 1s with x1. A x1. Then I have a 1 right here. And then I have a 0. And I have my epsilon, right? So now you'll see that every one of my production rules with more than one symbol, every single one has now only variables in it. Does everybody see that? So this is very important for us, because what we're going to do is we're going to be trying to push next out all of these extra symbols so I have at most 2. So you're going to notice I'm going to keep making these weird little changes, but each one is getting us incrementally closer to the Chomsky normal form. Does everybody see that? So each one of my major steps I'm going to do, I'm actually getting myself a little closer by enforcing another property. So now that brings me to the next property. Actually, not the next property, it's the next step of this. And we have to be very careful with this step. And I'll justify it when we get there. So the next one, often people like to call this bin. So what we're going to do is we're going to shorten bodies. And when I mean bodies of production, not me. Like I don't need to get any shorter, okay? So we're going to shorten bodies. With, so it says with, it's sort of melted between the W and the I there, with 3 symbols or more. So I would like to make sure that every production has only at most 2 symbols. I can use what I'm going to describe next to do this. So here's the idea. If I give you, say, for example, here, notice I have 3 here. I have 3 symbols. What I could do, now if you think about it, when I commit myself to applying one of these rules, I have to apply it entirely, right? I can't just be like, I'm going to only take this first part here, unless I had a rule for that, right? I have to commit myself to each one of these, meaning that it's really just a sequence of these symbols that I have to really look at. So here's an idea. What if I could take each one of these and do the following? Now I'm going to write it more generally in a moment, but suppose I had it this way. So suppose I could take A. So suppose I took that x0, A, x0. You'd agree with me that I could just say, okay, well, I'm going to create a new variable. I'm going to call it A1, for example. And what I could do is I could effectively just chain it along. Because you remember, once I commit myself to one of the production rules, I have to apply it in its entirety, right? So if I imagine I have my A over there, and I produce x0, A1, note there's a subscript there. I've introduced this new variable. Notice that I can hang on to the rest of it. And say, for example, just for hypothetical purposes, say if I had like 20 symbols in one production rule. Could you see by principle that I could keep this process going where I could just keep applying what I'm doing right here, where I read one symbol, I introduce a new variable. That new variable's production rule is going to end up being the next symbol, then another variable. Then I can introduce another one. And I can keep going until I have my last two symbols sitting in its own production rule. So now I've just chained them along all the way down. Isn't that neat? See, at first when I first learned about the Chomsky Normal Form, I thought that was really neat. Because you think, oh, well, how am I supposed to deal with this? Well, once you realize, oh yeah, I have to substitute using the entire production rule, right? So it means that I could obviously just introduce a substitution somewhere in between here. And I could kind of splice it all together as one big jagged path, if you think about it. Is that kind of cool? So let me write out how you do this more generally, and we'll come back to our example here. So some productions may have too many symbols. And I must stress that this process I'm going to describe, you can do it even when there's terminals that are present in the production rules. The rules still apply. It's just at our stage in this process, we can guarantee they're only variables. I'll come to that if we have time after this. I have too many symbols. So what do? For each production A, or imagine I have a bunch of symbols, U1, U2, all the way up to UK, where every UI is a variable. I must stress that doesn't have to be. So I just need to stress this, is that this process, I don't need it to be a variable. But in the context for which I'm demonstrating to you that you could build a Chomsky normal form out of any context-free grammar, it will be a variable. So where UI is a variable, and K is greater or equal to 3, you're going to replace A let's replace A, U1, U2, all the way up to UK with the following. You're going to have A produces U1, A1. A1 is going to produce U2, A2. Then A2 will produce U3, A3. And this process will keep going on and on and on until we got it long enough, such that the final one will be A sub K minus 2 produces UK minus 1, UK, where each AI is a new variable. Not very happy with that way. Let me fix that. New variable. So you're going to end up with this whole chain of production rules. So first, are we okay with this idea? So all I'm going to do is that if I have one that's too long, I'm just going to chop it up into segments of ones, or possibly a last one with two of the symbols of the production rule, and I'm going to introduce new variables to stitch them all together. Like a chain. You can think of it like a chain. And the great thing about this is because I introduced these new variables, I know that the other production rules are not going to cross with them. That's why I need those new variables. So let's think about this. So why don't we look at our example over here, and I'm just going to apply this idea I just used over here, and let me do it right here. Okay, so I have S0A, I have all of this, so that first rule is okay. It's really these two that are the problem, right? They're way too long. They have 3 symbols in them. So what I'm going to do is I'm going to introduce, I can introduce those production rules. So let's introduce, so let me take this idea I have over here. So remember, it has x0, a1, then it has a, x0. So I'm just going to replace this rule now because I have those two over there that represents this. I can go x0, a1, and now I'm just going to take the second part. I need to add that in here. So here's a new production rule using this idea. A1 is going to give me a x0. So I'm just using the idea I wrote over there. And now I have to do the same thing again, but with that production rule, right? So let's try this. Let's try this, everybody. So I need to have, I'm just going to call it instead of A1 again, because obviously I'm already using that name, so I better not do that. Instead, I'm going to call it I'm going to call it B1. The first symbol is okay to be there. That's the process we do this with. But now I need to make sure I have somewhere where all the rest of those symbols are going to be, because its length is 3. So the last 2 symbols of this production better appear somewhere. Well, it's just A, right? It's A, and then I have x1, right? So have we gotten rid of all the longer bodies? So everybody, tell me, are we okay with this step? So now every one of my production rules has at most 2 symbols. Does everybody see that? Are we okay with this? Give me a thumbs up if you got where we're going so far. So all I've done is I've eliminated all these extra length productions. So I must stress that this is mostly us just on the side thinking about it. That's the actual context-free grammar over here. So far. We're not done yet. We still got 2 more steps to go through. Like I said, this is an interesting process. Okay. So now we have everything so that, notice that all of these are pairs of variables if they have more than 1 symbol. But now we have this other issue. It's these epsilons. Notice that now this epsilon is not sitting up by the start symbol anymore. Does everybody see that? So before it wasn't a problem, but now it is. So I need to get rid of this epsilon production. So I got to tell you how to do this. This is easily what I would consider the toughest of the rules. So hopefully you can follow me with this carefully, because this is easily the trickiest one. Okay, so let's see here. So step 4. Step 4, I'm going to call this del epsilon. So we're going to eliminate epsilon productions. So while there is a production rule, so when I say while, that means you're going to repeat this process over and over again, just like you're thinking of like a while loop. You're going to keep repeatedly doing this process until the following. While there is a production rule, A produces epsilon, where A is not equal to the new start symbol that I have, we're going to do the following. So we have to be careful with this. So first step, you're going to remove that production rule. So you're going to remove A produces epsilon. That's the first thing you're going to do. Just get rid of it because we don't want that there. It needs to get out of town, okay? Out of here. Out of here. So next, for each production rule. So now this is the tricky part, and I want you to follow me carefully. I'm going to give you a couple of ideas of how this works, and we'll see the example. For each production rule R, where A appears in the body, we consider each combination of occurrences of A where one or more A's are omitted, meaning I don't include it, omitted in R. So I just want to give you some clarification of what I mean by this. So we're not going to run into this issue so much because of the way the Chomsky normal form is coming about so far in our process, but I just want to make sure I give you just a general flavor for what I mean. So for example, suppose this is just an aside. So it's just an aside. Suppose if it was that R is, say, U, A, V, where U and V were substrings of terminals or variables. What I'm telling you is that you're going to, so if this appears, you're going to add another rule where we're going to consider each one of the combinations where I'm going to consider removing A. So this is going to be the case you're going to run into most often. But notice that the form of our productions, you're just going to end up with possibly at most one symbol sitting every single time in a production rule. Every one you add. You don't remove this, you just add this new one. So just to give you an idea, just another example of this. Suppose if I had, say for example, if R, now we don't have it appear like this in our process, but it is very real and possible to have it so that if you were to apply this separately from some of the other steps I've done, and suppose you have it U, V, W, where these are different strings of terminals and variables, and you have these two appear, then you're going to add, then you would add three different rules. You would add R, where A, this first A doesn't appear. So you would have U, V, A, W. Then you would consider when this A isn't appearing, so you would add this rule. So you would have U, A, V, W. And then you would add a third one for when both A's don't appear. So that's what I mean by combinations of occurrences. So you'd have just U, V, W. So that's what I mean by combinations of occurrences. So you're just going to look at each one of these, and if you see an A, you're going to add it where every single time it doesn't appear. If it only appears once, it's really easy. It's just going to be simply, you're just going to add it without that variable there. However, if you have it where A appears more than once, you're going to have to consider all combinations of when that variable doesn't appear. So let me just give you a flavor for what we're going to do with this. I have more details, by the way, in the notes if you find yourself confused by this step, but I'm hoping you're following me just fine. So we're just going to add, so I'm just going to do what I just said a moment ago. Add a new production rule. Add a new production rule R. So notice I'm not removing anything. I'm just going to add new production rules. Add a new production rule R where it has the same form. Has the same form, but omits that combination of A's from the body. So that's what I did over there, if you're curious. When you're doing this, you're only going to really run into two real cases most of the time. You're going to run into the first one I mentioned there, where you're just going to remove an A or whatever variable that is. Or you're going to run into the second one I have right there. But you'll notice that because of the structure of our production rules, there's not going to be other strings kicking around, right? There's just going to be the two variables just sitting there by themselves. So you'll just remove one and then you'll remove both. But you might ask, okay, well, what happens if I remove all the symbols? So in my occurrences, note that if R, where A appears, R produces A appears, that means, of course, I have to remove the occurrence of A in this case. You're going to add production. You're going to add the following production. You're going to add R produces epsilon, unless, this is important, unless it was already deleted. Or be more precise, or it was previously deleted. So it means that you're not just going to try adding back in thing you already removed. That's all I'm saying. So I want to walk you through this process. Fortunately for us, we only have one epsilon kicking around. So you're going to see one round of this. But if there's many epsilon symbols, you're going to have to keep repeatedly of doing this over and over again. So that's why I'm saying this is a little bit of a tricky step. The next one after this, we may have time to get to it. If not, we'll do it next time. I think we have a few more minutes, so I might have time. It's the last step, by the way. We just got this one, and then that's just the final step. So let's do the example of me removing the epsilon. So let's get us moving on over here, and let's walk through this. Okay. Okay. So back to our example. Notice that A produces epsilon. That's the only example we have in our entire context-free grammar so far. So we're going to remove A produces epsilon. Then, now we have to look at everywhere where A appears. So now this is where you have to be careful. So I'm just going to kind of go boom, boom, boom through them, then I'll give you the context-free grammar here. So then we have to add production rules where A appears. There's going to be 3 spots where they happen. So the first one, of course, is where we had the start symbol, right? Well, we had this one, right? So what we're going to do is imagine we take away the A. That means that we have to put epsilon there because I've deleted all the symbols. So add S0. Now remember, S0 produces A will still be there. I'm just adding this in. You might ask, Dan, why does this rule work? You'll see when I get to the example of why this will do the trick. So if I have A1 produces AX0, there's only one A here, right? So I just have to add in where I don't include the A. This is what you're going to run into very often. And then, of course, I have A2. This is the same idea. I had AX1. I'm going to consider when I remove the A. So that means I'm going to add the rule. Sorry, not A2. It's B1, right? Let me see. Sorry, let me think. This is an. Let me think here before I get too ahead of myself. Yeah, it's A1 and B1. Yeah, that's right. That's right. A1 and B1. Because remember, we had our chains of productions we have. So now, I was just about to get ahead of myself and write A2, but it's actually B1. We have to always be careful when we're doing this. So what I need to do is I need to add in B1, X1, because remember, I just imagine I take away the A. And then here we go. Here we go. So now I had all of them. So then I'm going to say then, and then I'm going to write out everything I've got here with this change. So now I have A or epsilon. Remember, I added in the epsilon. Now A, it produces X0 A1 or X1 B1, or it produces 1 or 0. Notice that because these aren't affected by A anymore, right? Like these used to be A's, right? At some point, and then I made this chain. I don't touch these at all. They're new variables, right? Oh yeah, let me make sure that's clear. That's a 1. Okay, good. And now I'm going to add in my A1. Now remember, this one is just I have A X0, and I added in the X0. I added in X0 like this. And then I had B1. It's going to produce AX1 or X1. Remember, that's just what I'm doing. I'm just inserting these in. And I have the same thing I had before. X0 will produce 0. X1 is going to produce 1. So notice that now we're okay because now the epsilon is sitting up here. You're going to very often find when you're doing this eliminating epsilon productions, you're going to find that the epsilon is going to slowly, if it either doesn't go away, it's going to move up. If you think about it in that way, it's going to move towards the start symbol. And you might ask, Dan, why is that? Well, you might ask, okay, well, first, why does this work? So let me give you a very brief explanation, then we'll wrap things up here. So remember, before I had an epsilon sitting right here, right? I had the epsilon sitting right here. And you might ask, okay, well, Dan, where did it go? Like, how does this work? Well, remember, whenever I applied the rule A, I had the choice where I can include a 1 or a 0 or epsilon, or I can insert these, right? Well, remember that if I used epsilon, I very often use epsilon to terminate the generation of a string, right? Well, because the epsilon isn't here, I need some way when I apply A, which is why I look at all frequencies of when A occurs. Notice that whenever A appears, I include the version without the A. Just like I do right here as well. Just like I do right here. Notice that every single one of them, by having it where I omit that one symbol, now I have it where I'm basically simulating the epsilon by getting rid of it. I've introduced the option where the epsilon would have been. Is that clear, everybody? So now notice I've gotten rid of all the epsilon productions, but there's really just one step left, and we're going to do that next time. Notice that there's still one other issue. Notice that if I look at some of these, notice I have an X0 and an X1 here. Those are variables, right? They need to be terminals in the Chomsky normal form. So we need to, we still need to resolve the variable unit productions. Those we still have to deal with. So we'll deal with those next time, okay? So when we come back, we'll do the last step of the Chomsky normal form. And I will include this final step in the notes. So if you want to read ahead, you're welcome to. I'll also include another example. So if you want to walk through this yourself with another example, or I recommend picking up one of the ones we did earlier and try this out, okay? So when we come back, we'll look at this removing of variable unit productions, and then we'll wrap things up with this. Then I'm going to move on to some more exciting content we're going to start talking about another finite automaton with a stack. Is that kind of neat? So we're working our way up. So that being said, I want to say thank you very much and have yourself a wonderful weekend. I'll see you later.